So, welcome friends to this session, which again we will continue for the discrete time optimal control system. In the previous class we have seen that how a Lagrangian we can represent in the Hamiltonian form, and all discrete EL equation we can write in terms of the Hamiltonian form. So, these three EL equation, which is with respect to x k, which will give me the co-state equation, optimal control and the state equation. If we will write these in terms of the Hamiltonian, we get del h by del u equal to 0, del h by del x equal to lambda kx, and del h which is at point k minus 1, uk minus 1 and lambda k give me the xk. So, to get the proper form, we convert the second equation as x star of k plus 1. So, we get all functions of h in terms of the x star k, u star k and lambda star of k plus 1. So, we have defined the Hamiltonian as h half of x prime qx, half of u prime ru, lambda prime k plus 1 as ak xk plus bk uk. So, by this basically we have to find out our control equation. So, if state equation and co-state equation. So, if I will write the state equation, how we write this? Del h. So, I am writing this as h dot, del h dot, then I have to differentiate this with respect to lambda k plus 1. This means what the x k plus 1, x star k plus 1 we have taken as del h by lambda star k plus 1. So, this means I have to differentiate this with respect to my lambda k plus 1, and this gives me nothing but my x of k plus 1. So, if I will differentiate this with respect to lambda k plus 1, first two term are independent of lambda, this is lambda prime k plus 1. So, nothing but by this differentiation I will get ak xk plus bk uk, which is nothing but my state equation. Co-state equation, how I will get? My co-state equation is this, I will write this is lambda star k. So, this is lambda k is nothing but my del h by del x of k. This is my del h by del x of k. So, with respect to x k I have to differentiate. So, my first term is the function of this. So, this will give me, it is a quadratic term q k x of k, second term independent of the x, and in the last term I get only the first term, which is the function of x. So, this give me plus A transpose k lambda k plus 1. So, this will be my co-state equation, and the third is my control equation, which is del h by del u, del h by del u of k is equal to 0. So, this means I have to differentiate this with respect to uk. I will get from here So, this implies if I will differentiate this with respect to u, so this give me r k u k, and in the second term my this term is the function of u, this give me plus, I am differentiating this b prime k lambda k plus 1 equal to 0. So, by this I get my state equation, co-state equation as well as my control equation. So, I get my state equation as x star k plus 1 as a k x k plus b k u k, my co-state equation as lambda star k as q k x k plus a prime k lambda prime k plus 1, and control equation is r k u k plus b prime k lambda k plus 1 equal to 0. So, directly I can write the value of u from this as minus r inverse b prime lambda k plus 1, and this u star k if I will place in my state equation, this will be x star k plus 1 as a k x k, b k, in place of u k I am writing r inverse b prime lambda k plus 1, and I am defining this b prime r inverse b k r inverse b prime as E. So, if E is defined as, so my lambda x star of k plus 1 is a k x k minus E k lambda k plus 1. So, we have taken u k as minus r inverse b prime k lambda k plus 1, this we have taken as the u, and we are writing x star k plus 1 as a k x k minus E k lambda k plus 1. This we are writing from my state equation. So, just for simplicity I am dropping this star from all the writing, where E is nothing but my b k r inverse k x k b k, and my co-state equation I will take it as such, which is my lambda k q k x of k plus a prime k lambda k plus 1. This is my co-state equation which we are taking directly. Now, by combining these equation I can write my Hamiltonian system as x k plus 1 lambda k as a k minus E k q k a prime k, and this will be x k and this will be lambda k plus 1. So, now if we will analyze this equation, x is at the instant k plus 1 and lambda is at the instant of k. This we are expressing in terms of the x k and lambda k plus 1. So, this is my Hamiltonian system, and what will be my boundary condition? Our boundary condition is del L at x k minus 1, x k u k minus 1 lambda k differentiated with respect to xk and del s by del xk at the point k0 to kf, this must be equal to 0. K0 is known to us, so delta x of k0 will be 0, so that term will vanishes and we are left only with the k equal to kf term. Now Lk is h of xk uk lambda k plus 1 and we have to differentiate L of k minus 1. So this means my h will be a function of x of k minus 1, u of k minus 1 and lambda k. This means the difference, once I will differentiate this with respect to xk, so my this term will give me the 0 value. So I am left, and what I have here at k minus 1 point, this is lambda star k x of k, and this give me only minus lambda star, and this term is similar del s by del x of k, delta x of k equal to 0, s is nothing but my half of x prime f of kf x of kf, and if I will differentiate this, so at kf point my lambda of kf equal to del s of x of kf, kf by delta x of kf. If this s of kf I will differentiate with this, so I will get nothing but lambda kf equal to f of kf x of kf. So my boundary condition for this is lambda kf is f of kf x of kf. So this is my boundary condition. So if you recall, this is similar like we got in the continuous time system. So from here we can have a relation between lambda and x. We can assume a relation between lambda and x. So I can write, so we can say, let us consider the transformation as lambda t equal to some unknown matrix, lambda k equal to some unknown matrix pk xk. So which can transform my lambda into x. So we can consider as my lambda star k equal to pk xk, and this will lead further to a Riccati equation. So I stop my this session here with the consideration that we can consider lambda k as pk xk, and this can be further leads to a matrix difference Riccati equation. So we have considered lambda k as pk xk. So now my state equation, if I will write this as x of k plus 1 as ak xk minus ek and lambda k plus 1, this lambda k plus 1 I am writing from here as pk plus 1 x of k plus 1. So in my state equation lambda k plus 1 I have replaced by pk plus 1 x of k plus 1. So by this I can solve this equation as I plus ek pk plus 1 x of k plus 1 as ak xk. So, if I will pre-multiply with the inverse of this, I can write simply my xk plus 1 as I plus ek pk plus 1 inverse ak xk. So, this is my x of k plus 1. So, this means I am writing this x star k plus 1 as I plus ek pk inverse ak xk. So, I will keep this last equation and I will consider now my this state equation, sorry, co-state equation, which give me lambda k I will take as pk x of k, in place of lambda I am writing plus, sorry, this equals to my qk, keep as such xk plus a prime k. What is my lambda k plus 1? pk plus 1 into x of k plus 1, this is x k plus 1, because this lambda k plus 1 I am writing as pk plus 1 x of k plus 1, and this x of k plus 1 I am replacing by this expression I ek pk plus 1 inverse ak xk. So, this xk plus 1 I am replacing with I plus ek pk plus 1 inverse ak xk. So, what is the advantage here is my all terms are in terms of the xk now. So, I can eliminate xk from this equation to get pk qk plus A transpose k pk plus 1 I plus ek pk plus 1 whole inverse ak. xk is eliminated. So, now my this equation is in terms of the pk, qk, pk plus 1 ek, and ek is nothing but my, what is my ek? B R inverse B prime. So, this means I can solve this equation in terms of the pk, because all other terms are known. So, I have my equation as pk equal to a prime k pk plus 1, a prime k pk plus 1 I plus ek pk inverse ak plus qk, and this is called my matrix difference Riccati equation. And this Riccati equation, because we know we have the lambda Tf as f of Tf, x of Tf. So, by this I can say my P of Tf is nothing but f of Tf. I have my terminal condition. This is a difference equation which can be solved for pk with the terminal condition as, sorry, this I have written in the continuous form, but here we will have a discrete form which will be as lambda kf as this is f of kf multiplied with x of kf, and this will give us p of kf as f of kf. So, this is my Riccati equation which can be solved with the terminal condition as p of kf as f of kf. And alternatively, this equation I can also write in the form as, if I will take this pk inside this bracket, so this is the same equation as qk plus a prime k, pk I am taking inside, p inverse k plus 1 plus ek whole inverse ak. So, any form we can take, we have pk as a prime pk plus 1 I plus ek pk inverse ak plus qk, or pk as a prime k p inverse k plus 1 ek inverse ak plus qk. So, this is my difference Riccati equation which can be solved for pk using the boundary condition as pkf equal to f of kf. So, once pk is known, I have to find out my control law. What will be my uk? So, my uk is R inverse B prime lambda k plus 1. So, now we have to see how we can represent u in terms of the p. So, we know my co-state equation is lambda k is qk xk plus A transpose k lambda k plus 1, and lambda k if I will replace as pk xk, this is qk xk plus A transpose k lambda k plus 1. So, now I can write this lambda k plus 1 in terms of the xk. If I will write A transpose k lambda k plus 1 as pk minus qk xk, and lambda k plus 1 is nothing but, so this I will write as A minus T pk minus qk xk. So, this A minus T is what? What is this? This is the inverse of A transpose. So, this is inverse of A prime. So, if this is my lambda k plus 1, I can write my U as U star k as R inverse B prime k, and lambda k plus 1 I am replacing as inverse of A transpose multiplied with Pk minus Qk into Xk. This means I am representing my Uk in terms of the Xk, so that I can utilize my closed loop control. So, I can have the state feedback as X of k, this R inverse B prime A minus transpose of the A inverse Pk minus Qk, this I can define as my L. So, if this is defined by Lk, I can simply define Uk in terms of my Lk Xk, where Lk will be my controller gain, which is given as R inverse B transpose inverse of the A transpose Pk minus Qk. So, by this I can design my optimal Lk, which is giving me the optimal value of the U for a closed loop control system, and if I will use U equal to minus Lk, so my closed loop system equation will be X star k plus 1 Ak minus Bk Lk X star k. So, by this I can get my closed loop control. Say in this form of the Riccati equation, where I have to use P inverse k plus 1, and in U I have to use the inverse of the A transpose. So, for this, if the inverse of the A transpose exists, this means my matrix A should be a non-singular matrix. So, if A is a singular matrix, then the inverse of the A will not be possible. So, this problem we can eliminate utilizing the alternate form of my Riccati equation, which we will discuss in the next class. So, today I stop my discussion at this point. Thank you very much.